Hello, I am Hettie Schönfeldt, Faculty of Health Sciences at the University of Pretoria. I'm a Tier 1 Chair in Nutrition and Food Security and member of a United Nations high-level panel of experts on food security and nutrition. In this lesson, we will explore the principles and applications of food composition data. To start with, what is food composition data? Food composition data entails detailed information on the molecular, chemical, and nutritional content of foods. This knowledge is typically organized into tables and more recently into databases. Food composition data can be classified based on macronutrients, micronutrients, and secondary metabolites, also known as bioactive compounds. Food composition data is used by diverse stakeholders across food systems as it provides essential insights for a variety of applications in food, agriculture, health, and nutrition. Next, let's explore the evolution of food composition data. The knowledge of food composition started in ancient times and has evolved throughout history with the advancement of technology and scientific analytical capacity. Early records of ancient civilizations, Mesopotamia and Egypt, show some understanding of food properties, like energy from bread and meat. Hippocrates and Galen wrote about food properties and their health effects, but there was little scientific basis. Hippocrates is often attributed with a well-known quote, "Let food be thy medicine and medicine be thy food." This phrase reflects the ancient belief in the healing power of food and its integral role in maintaining health. From the 17th century on, the systematic study of food composition started to be established, driven by advances in chemistry and a growing interest in understanding the nutritional and medicinal properties of food. Early work focused on identifying the basic components of food through rudimentary chemical analysis. One of the earliest milestones in this area was the identification of caloric energy in food. For example, in the 18th century, Antoine Lavoisier laid the groundwork for nutritional science by studying respiration and metabolism, linking food consumption to energy production in the body. During the 19th century, there were many advances, such as the clarification of food energy production and the identification of 3 macronutrients: carbohydrates, fats, and protein, as well as their physiological role. For example, Carl von Voigt's research highlighted the importance of systematically studying food composition and its effect on metabolism. This work influenced the development of food composition tables and early dietary guidelines, which became critical for public health and nutritional policy. The first composition tables began to emerge fueled by such research, finishing the century with the publication of Atwater and Woods, The Chemical Composition of American Food Material, by the USDA, also known as the United States Department of Agriculture, in 1896. In the 20th century, the methods of analysis and the elaboration of food composition tables were improved in many countries. The development and adoption of mass spectrometry and other analytical techniques began to emerge in the 20th century. The concept was introduced by a Russian botanist who used it to separate plant pigments. These improved analytical techniques allowed for the identification and quantification of macronutrients, again carbohydrates, fats, and proteins, and our micronutrients, vitamins, and minerals. Additionally, these methods and other analytical techniques enhance the ability to detect and measure trace nutrients and contaminants. Today, the study of food composition integrates diverse scientific fields to address complex questions about nutrition, health, and sustainability. Food composition data provides essential insight into food quality, including ecological, nutrient, health, safety, and sensory properties that deepen our understanding of what we eat and how it affects both human and planetary health. As populations grow and diets shift in response to climate change, leveraging food composition data is essential to building healthy, resilient, and sustainable food systems that benefit both people and the planet. In the remaining lesson, we will explore the diverse applications of food composition data across food systems. For example, farmers and breeders can leverage food composition data to breed and select crop varieties with enhanced nutritional, sensory, and environmental traits. Food composition data is crucial for food processing and product formulation, particularly in the development of sustainable and healthy foods. Food composition data is crucial for ensuring food safety, as it plays a significant role in detecting contaminants, monitoring nutrient stability, and maintaining quality throughout the food supply chain. Understanding the nutrient density of various crops and food sources helps in promoting sustainable agricultural practices, such as biofortification, that is not only enhancing food security, but also improving the nutritional content of crops. Food composition data guides food processors in selecting methods that retain the maximum nutritional value of foods, such as choosing the best cooking, drying, or preservation techniques and minimizing nutrient loss. In dietary surveys, aggregate food consumption data, for instance food frequency questionnaires or national dietary surveys, is combined with food composition data to estimate average nutrient impacts. Analysis of dietary patterns and their adherence to dietary recommendations, like the Mediterranean diet or the DASH diet, relies heavily on accurate food composition data. Data from epidemiological studies are used to design and assess the impact of dietary interventions, for instance, reducing salt intake to lower blood pressure, or the supplementation of babies with vitamin A, as well as to educate consumers on strategies to improve diet quality. A broader and deeper understanding of the composition of underutilized traditional and indigenous foods can help identify opportunities to support nutritional needs in sustainable and culturally acceptable ways. Additionally, addressing the growing burden of diet-related diseases is even more complex in practice and requires a more expansive and holistic understanding of food composition beyond the essential nutrients. Therefore, to establish the relationship between diet and health, but also for monitoring and evaluation in public health nutrition, the need for reliable information on the composition of foods, locally to globally, is indisputable. Nutrient databases in many countries face significant challenges in verifying their accuracy due to several key limitations. These include restricted information on a limited number of mostly raw foods and incomplete nutrient coverage for each food. Additionally, many databases contain outdated and unreliable data, lack information on underutilized nutrient-dense foods, and have incomplete food descriptions. The data came from diverse providers using various methods, often selected based on availability rather than relevance. Gathering and curating more and better data is essential to the mitigation of further nutritional and health problems and to solve those already experienced. There is an evolution occurring to measure more foods and food components, leveraging emerging technologies to expand our understanding of what is in the food we consume. We know that diverse crops and animal species provide varying levels of essential macro and micronutrients like carbohydrates, lipids, proteins, minerals, and vitamins. However, the composition of food goes far beyond these well-documented nutrients. In particular, food composition data efforts are increasingly mapping the unique secondary metabolites, also known as specialized metabolites, phytochemicals, or bioactives, along with contaminants that enter through production, processing, and preparation practices that are in food that impact our health. Globally, data on the presence and amount of these compounds has been limited to a small number of foods, limiting our ability to apply these data to assess dietary intake, formulate healthy diets, educate consumers, formulate policies, or influence the food industry. Furthermore, a vast number of food components are yet to be identified or quantified, and efforts to map this nutritional dark matter are emerging. Current quantitative analysis of compounds in foods, particularly vitamins, carotenoids, sugars, and other phytochemicals, involves dedicated and targeted methods. These methods aim to accurately measure the concentration of specific compounds in complex food matrices. However, this analysis comes with limitations, particularly related to the availability and cost of standards, as well as biases towards known compounds. The limitation of traditional targeted analytical methods can be overcome by leveraging advanced complementary techniques, optimizing methodologies, and fostering collaborative efforts to develop comprehensive and standardized approaches for quantifying a broad spectrum of compounds across diverse food matrices. Foodomics can build on traditional compositional analysis by expanding the aperture of food composition and providing a more comprehensive understanding of biological systems and disease mechanisms related to food. This is an exciting time, and we have a tremendous opportunity to leverage the science of food composition analysis, using both traditional and emerging techniques to revolutionize health and nutrition research, food safety, sustainable food systems, and personalized health care, ultimately contributing to improved public and planetary health.